Hi, I'm Chris Hopkinson, Professor of Geography and Environment at the University of Lethbridge. Today I'm going to talk about our innovations in environmental monitoring in the headwaters of the Oldman River Basin. Here we see the location and outline of the Oldman Drainage Basin upstream of Lethbridge with 5 of our airborne LiDAR monitoring sites outlined. The headwater region is where most of our water originates as snowpack, which typically melts off over a prolonged period due to the elevation range and forest cover in the mountains. For the Water Innovation Program, most of our activities have centered on the West Castle watershed, where we have an established field station, field plots, and telemetered hydrometeorological instruments, all of which are also supporting our airborne multispectral laser scanning research and monitoring. Here we are at the University of Lethbridge West Castle Field Station, which is where much of the work I'll showcase today has taken place, or started. Through the Water Innovation Program, my grad students and I have developed and tested innovative LiDAR, LiDAR, and photogrammetric techniques to evaluate long-term forest vegetation changes or to monitor winter snowpack across the entire West Castle watershed. The techniques we have developed have integrated field plots, weather station data, and LED-based ranging, as well as remote sensing imagery to deliver a comprehensive understanding of watershed dynamics across seasons and over decades. Over the next 20 minutes, my students and I will share with you some of the developments from the work in the castle, and as well, we will illustrate how we are building on what has been learned to study the impacts of the Kino wildfire on vegetation recovery and montane water resources. And finally, I will end with some thoughts on our vision to utilize this framework in a community-based monitoring context. First, we will examine some remote sensing innovations in forest mapping and monitoring undertaken by Maxim, Thomas, and Dave. Second, we will explore Kelsey and Celeste's innovative research into snowpack monitoring and modeling using LiDAR and LED ranging. Then, we shift location to Waterton Lakes National Park, where Jesse and Travis are tracking the early stages of forest ecosystem recovery following the Kino wildfire of 2017. And finally, we travel slightly downstream to join Danica as she explores the co-creation of knowledge using LiDAR and indigenous wisdom with Piikani First Nation. Given LiDAR plays a prominent role in my lab, we start with Maxim for a summary of our recent multispectral LiDAR research.
I have flown and processed multiple LiDAR datasets over Castle and Waterton. The summertime surveys provide a baseline DEM for snow mapping as well as information about vegetation change in the headwaters. In 2016, I designed and installed radiometric calibration targets to calibrate multispectral LiDAR intensities and derive reflectance values to help characterize vegetation in the West Castle.
Multispectral LiDAR is just like regular airborne LiDAR in that we can derive terrain and canopy height or canopy cover models, but due to operating at 3 different wavelengths, we can also generate colorized 3D imagery. And as an example, here we see a 3D laser composite image of the Wapta ice fields in the headwaters of the Bow River. Such images may be impressive, but as this is a new remote sensing technology, there are no standard calibration routines to provide actual laser reflectance. Furthermore, channel intensities can be ratioed to provide vegetation indices, but early experiments have demonstrated that such indices could vary with flying height or terrain elevation. Using accurately surveyed and spectrally calibrated 3-dimensional targets, Maxim devised a routine to radiometrically correct the 3-channel intensities and thus mitigate altitude effects and therefore derive new multispectral LiDAR vegetation indices. Taking this to the 3-dimensional realm allows us to compare the distribution of canopy spectral properties within the vertical canopy profile. As each wavelength responds differently over leafy and woody biomass, we can once again ratio the channel intensities to provide a cross-section or voxel-based vegetation index. Now, all of this may sound esoteric, but the real value in these 3D spectral data is that we can derive structural and spectral signatures of land cover types, including vegetation species, and therefore, using a single sensor, generate a high-resolution and high-accuracy feature classification map. So, let's change scales now and check in with Thomas to see some of his innovations in UAV monitoring.
My studies involved using time series UAV ortho imagery and structure from motion point clouds. We use these to track montane forest ecosystem changes in the Castle and Waterton headwaters. In Castle, we were monitoring trail restoration, while in Waterton, we were tracking early stage seasonal recovery of forest ecosystems following the Keenan wildfire of 2017. These UAV images and models provide an invaluable archive documenting the regeneration of forest ecosystems after disturbance.
Here we see Thomas piloting his UAV over a trailhead in the castle during a trail disturbance recovery survey. Instead of castle, however, I will summarize some of the UAV post-fire recovery monitoring efforts in the nearby Cameron Valley of the Waterton Lakes National Park. The image at right illustrates the extent of severe wildfire forest loss in the Cameron Valley, and at left you can see one of the early UAV ortho images captured in spring after the Keenan fire. Note the highlighted low-lying areas where snow accumulates and how these areas approximately correspond with new vegetation growth during the summer. See how a UAV greenness difference image clearly delineates these areas of new growth. Also, using artificial intelligence algorithms in the Picterra software platform, it is possible to identify and extract individual down stems. Of course, a benefit of UAV data is the ability to construct three-dimensional point clouds using structure from motion. Here, the post-fire landscape dynamics are clearly visible in this comparison of SFM surfaces from 2018 to 2019. Morphological changes due to vegetation growth, down stem movement, and terrain erosion can be easily discerned. So let's check in with Dave now to examine forest cover changes over a much longer timescale.
I studied a century of land cover change in the West Castle watershed using LiDAR and repeat photography. Land cover is an important input into hydrologic models. Using machine learning techniques, I found that change in land cover in the alpine treeline ecotone was primarily driven by aspect-specific patterns of regrowth after high-elevation forest fire.
Dave used the University of Victoria Mountain Legacy Project image archive for West Castle to document forest changes from 1914 to 2006. A wildfire passed through the castle in 1936, so some changes are due to this fire, such as the treeline reduction here, and some are due to more gradual successional or mortality processes. To convert these oblique photos into ortho images, Dave used the Airborne Lidar to create an accurate surface upon which they could be draped and manually classified into zones of forest cover. From the draped forest cover images, a change classification was derived for about 40% of the watershed. Stratifying by elevation shows that losses to tree cover are greatest near treeline, but there is also evidence of treeline advance into the alpine zone. Examining the aspect influence shows a clear tendency for forest cover loss on south slopes and new growth on north slopes. To use these change data in further analyses required that we gap fill the 60% of the watershed that was not observed in the Mountain Legacy Project archive. This was achieved using a random forest model trained with the observed changes and driven by 9 terrain, land cover, and climatological predictor data layers. Combining the observed and simulated change products provides a spatially continuous map of century-scale forest change for use in further hydroecological or climatological studies. Now to a critical resource for those of us here in southern Alberta, one that varies quickly in space and time. We'll start part 2 with Kelsey to explore innovations in snowpack monitoring.
My research explored LiDAR snow depth modeling and quality control in the castle. Sensitivity analyses under midwinter and melt onset conditions confirmed well-known snow depth distribution trends, as well as the utility of LiDAR for seasonal snow mapping. I also employed machine learning to see if watershed-scale snow depths could be simulated and dominant snow depth drivers identified. We hope this work provides a basis for future headwater snowpack monitoring in Alberta.
Multiple LiDAR snow depth models collected over West Castle since 2014 were divided into midwinter and early ablation periods to evaluate the consistency of depth drivers at the 100 km² watershed scale. A random forest machine learning routine was set up both to assess the efficacy of operational snow depth simulation and to check whether the order of driver importance varied from the accumulation to the ablation periods. Despite the obvious depth variations between mid and late winter, elevation was consistently the dominant control at the watershed scale, with maximum depths occurring in the treeline zone between about 1900 and 2200 meters above sea level. Indeed, the data suggest treeline acts like a pivot point such that depth accumulates quickly in this zone and persists with limited variation while valley snow melts out and alpine snow continues to accumulate. The random forest analysis suggested that depth drivers were consistent across winter, with the order of importance descending from elevation to aspect to canopy to terrain morphology. The deepest snowpacks tend to occur in canopy openings on the north slopes at tree line, while the shallowest depths occurred on south slopes or under dense canopy. So now we know more about snow depth controls in the headwaters of the Oldman, let's check in with Celeste to see how watershed snow mapping can be operationalized.
My research is to map snow water equivalent using in situ LED and airborne lidar snow depth combined with snowpack density modeled from weather station data. To operationalize this framework, I am developing an airborne sampling and machine learning procedure that scales up to entire watersheds. This framework will create spatially explicit estimates of SWE for input into operational hydrologic models.
We've seen from Kelsey's work that LiDAR snow depth mapping works for a 20-kilometer long watershed, but the eastern slopes of Alberta span around 700 kilometers, with about 200 of that draining into the Oldman. So the challenge then is to devise a snow mapping framework that can be scaled up to all eastern slopes headwaters. The obvious strategy is to use sampling, such that for the time it would take to survey the West Castle, we might cover the entire Oldman headwaters. To test this approach, Celeste has designed sample flight lines across the West Castle using a least cost path analysis to cover most of the dominant snow depth driver classes. Then, using random forest imputation, snow depth for the remaining watershed area can be imputed. Initial results are encouraging, with watershed-scale test data producing an R-squared of 0.66 and RMSE of around 3 centimeters. To convert depth to snow water equivalent, or SWE, Celeste is using our elevation and spatial distributed weather station network in the castle to devise a watershed-scale density model. This is a work in progress, but as part of this framework, Celeste has also built and tested a prototype LED snow depth profiling sensor. The LED Ranger has 16 beams and has been co-located with other depth and energy balance sensors throughout 2 winter seasons. Results match or exceed the accuracy of similar depth sensors, but also provide snow texture and surface intensity. A next step is to explore possible commercialization. Now that we have a sense of the techniques we're employing for headwater monitoring, let's go to part 3, where we'll hear from Travis and Jesse and their research into eco-hydrological feedbacks following Montane wildfire. But first, a few words from Laura.
Here we are at one of our vegetation plots in the Acamina Valley. What we're particularly interested in is regenerating vegetation, especially pine.
My thesis builds on the snowpack and treeline research carried out by Kelsey, David, and Celeste in the West Castle. I'm using airborne LiDAR to study the impacts of vegetation recovery on montane hydrology following the 2017 Keno wildfire in Waterson Lakes National Park. This work will create a model of forest regeneration and snowpack feedbacks to help with water resource forecasting throughout the Oldman watershed.
As with West Castle, we are flying multispectral LiDAR over the slightly smaller Cameron Valley directly upstream of the Wardston town site to monitor forestry ecosystem change. Since the Keno fire in September 2017, we have flown 1 winter and 1 midsummer survey each year to track changes in terrain surface, standing dead trees, new growth, and snowpack distributions. As the burn severity map shows, we chose the Cameron Valley as almost all the vegetation and organic soil was lost, and the ecosystem must now re-establish. From the observations in Dave and Kelsey's work, we derive a conceptual understanding of the Cameron Valley hillslope snow and forest cover, such that under a mature forest scenario, snow depth peaks at high elevation tree line and plays a role in providing meltwater nourishment through the growing season. When the forest is removed by fire, we expect the zone of peak snow depth to move downslope, but the piece we wish to explore is how snow accumulation and tree cover interact during the tree line recovery phase. It's still early days in Travis's PhD research, but using the multispectral LiDAR, we will track biomass growth progression upslopes for the first 5 years post-fire and attempt to identify the snowpack to regeneration feedbacks and their variation with elevation and slope aspect. Continuing the theme of post-fire hydroecological interactions, let's check in with Jesse now to learn about his work along the Cameron Valley floor.
I'm using multispectral lidar and field plots to map the distribution of live and dead tree carbon in the Cameron Valley. I'm quantifying the influence of topography and riparian buffers on the rates of vegetation regeneration and tree fall within the valley floor. My study will contribute to the understanding of montane ecosystem recovery trajectories following severe wildfires.
Here we see close-up LiDAR surface models of the Cameron Valley floor where most of Jesse's ecosystem recovery and stem deadfall monitoring is focused. Field data are used to calibrate LiDAR models and then scale up to the entire valley. For example, field observations of stem count and deadfall are used to corroborate LiDAR maps of stem loss. Similarly, multispectral LiDAR imagery are being used to track new biomass growth, which is calibrated from plot measurements. Jesse is particularly interested to see if field-observed growth can be observed in either the active NDVI or NBR indices produced from multispectral LiDAR. At each of the field plots set up by Dr. Laura Chasma, Jesse is collecting height, cover, and photo-based indices of vegetation greenness. Results from 2018 are favorable, showing some correlation between plot-based greenness and LiDAR-based NDVI. 2019 and 2020 are yet to be processed, but so far it looks like multispectral LiDAR images will allow tracking of forest regeneration throughout the Cameron Valley. Okay, so now that we've explored some of our watershed monitoring innovations in the headwaters, let's travel downstream to where the prairies meets the foothills and check in with Danica to learn about her work with Piikani Nation.
My thesis synthesizes Piikani Nation's indigenous knowledge with remote sensing observations of their traditional lands. I'm using multispectral LiDAR to seek out culturally significant features and areas. Results from this project will provide a baseline for land use planning and environmental stewardship, as well as produce a 3D physical interactive map for community-wide knowledge dissemination.
It's early days in Danica's thesis and in our relationship building with Piikani Nation, but as a first step we checked the available LiDAR archive for Alberta and found the Piikani reserve lands had not been surveyed. Therefore, this summer we flew our multispectral LiDAR over the polygons shown here in red. So let's take a closer look at the floodplain area that we know is of cultural and historical importance to the community. As you can see, a LiDAR point cloud contains many structural and image-based attributes, but with the multispectral LiDAR we are most interested in the 3 intensity channels, from channel 1 in the shortwave infrared, channel 2 the near infrared, and channel 3 in green. Danica will use these data and community interviews for digital archaeolandscape mapping, the end goal being the co-creation of both online and physical 3D interactive maps to record and disseminate a cultural landscape history of these Piikani lands. Well, that concludes our whirlwind tour of my lab's research and innovations in the Upper Oldman Drainage Basin. So let's take stock of what we have learned and where we hope to go next. As you've seen, a common element in all of these studies has been the fusion of airborne remote sensing with boots-on-the-ground observations. And we've learned a lot about the dynamics of our headwaters and the innovative ways that we can monitor them. Our primary take-home message regarding headwater dynamics is that treeline can simultaneously advance, upslope, or retreat depending on aspect-based moisture limitations. This has important implications for future water resources, because treeline is the dominant watershed-scale control on snowpack, both during accumulation and melt periods. We are also discovering and implementing new approaches, both for multispectral LiDAR and UAV-based headwater monitoring. However, the real innovations are the fusion of these technologies with machine and deep learning frameworks for efficient inventory of post-fire tree stems or for regional snowpack sampling and imputation. So, where do we hope to go now? Well, we still have a lot to learn about the post-Kino fire montane ecosystem recovery, so we're keenly interested in getting a handle on the valley floor and hillslope snowpack to forest cover feedbacks and their associated impacts on the downstream water resource. And finally, an area of growing activity and need is the fusion of geospatial data with community knowledge and capacity. We're currently using these approaches to co-create a holistic understanding of landscape physico-cultural dynamics with Piikani Nation, and we see this as a potential model for future Guardian-style stewardship within our shared headwater environments. So, thank you for your attention, and I do hope that our presentation has been informative. Bye for now.